Conjugate gradient can solve an n-dimensional linear system in at most n steps in exact arithmetic. Here is the reason. We want to solve ax equals b, where a is symmetric positive definite. The same solution is the unique minimum of this quadratic function. Its gradient is ax minus b, so the minimum satisfies exactly the original linear system. At each point, the residual is the negative gradient, so it points downhill. Plane's steepest descent follows the current residual, but on a stretched bowl it can zigzag and revisit old work. Conjugate gradient moves along a carefully constructed search direction pk. Different search directions are conjugate with respect to a pi transpose a pj equals 0. Because a is positive definite, you transpose a Vx as an inner product. Ordinary orthogonality fits circular geometry. A conjugacy fits the stretched geometry of this quadratic. Each conjugate direction removes an error component without restoring components already removed. The step length alpha k chooses the minimum of the quadratic along the current search line. At that point, the directional derivative along pk is 0. Equivalently, the new residual is orthogonal to the direction just optimized. The next search direction combines the new residual with a correction along the previous direction. The standard beta coefficient is the new residual norm squared divided by the old residual norm squared. One iteration minimizes on the current line, measures what remains, and builds a new direction that protects earlier progress. After k steps, xk is the best point in the affine space spanned by all directions explored so far. Let ek denote the difference between the exact solution and the current iterate. Because xk is optimal over the explored space, its error is a orthogonal to every direction already used. Now comes the key fact: non-zero A-conjugate directions must be linearly independent. Suppose a linear combination of the directions equals 0. Multiply that equation by pj transpose A. Conjugacy removes the cross terms. Since pj transpose A pj is positive, cj must be 0. Therefore, every non-zero search direction contributes a genuinely new dimension. But our n can contain at most n linearly independent directions. After n non-zero conjugate directions, their span must be all of our n. The final error is then a orthogonal to every vector in the whole space. Choose the test vector v to be the error itself. Then en transpose A, en equals 0. Positive definiteness says this can happen only when the error is 0. So xn is the exact solution. The finite termination proof assumes exact arithmetic. Real floating point calculations gradually lose perfect conjugacy. In practice, old components can leak back, and the method stops when the residual is small enough, not exactly 0. The error after k steps can also be written as a polynomial in A applied to the initial error. Conjugate gradient implicitly chooses the polynomial that minimizes the remaining error in the A norm. If A has only m distinct eigenvalues, exact conjugate gradient terminates in at most m steps, even when m is less than n. Conjugacy gives independence. At most n directions fit, and spanning the space forces 0 error. Conjugate gradient finishes when an n-dimensional space runs out of new conjugate directions. That is the n-step theorem.